Yeah, no, I got consistency.
I know they all are.
And then right here, he was like.
Yeah, we're done with that.
Oh, okay, you said that. Those people.
All right, guys, I think I got the cameras rolling here and it is 4 o'clock, so I think I'll go ahead and get started. Hello and welcome. I hope you guys are doing well this week, hopefully better than I am. I actually sound worse today than I did on Tuesday, but the good news is I actually feel a little bit better. So it's been up and down a little bit. It's not been the easiest time, but I'll get some rest soon, I hope. I did spend a little time between the last class and this one, just kind of looking at where we're at as far as how the rest of the semester is going to lay out. So I, as of this morning, I think, I went ahead and published all the rest of the homeworks for the rest of the semester. There's only about 4 or 5 homeworks to go in these last 4 weeks. And they're going to feel a little more spaced out, actually, which will be kind of nice because we're in pretty good shape as far as that goes. But anyway, so the homeworks are updated now. In terms of what's going to be due soon, section 8.2 is the next homework. That's number 20, I believe. And that was supposed to be due tomorrow night, but I decided to give you until Saturday night to do it because it's a very short homework, but it is going to be based on what we're going to cover today. I realize we haven't really covered this section enough for you to have really gotten very far with this assignment yet. So it's a quick turnaround. Once you know how to do these problems, though, you're going to see that they go really quick. It's really pretty straightforward. So that's coming up for Saturday. So homework number 20. This is going to be due on Saturday night. Now, normally on Saturdays, I don't have office hours, but based on how I'm doing, I am pretty sure I'm not going anywhere this weekend. I'm just going to rest a little bit. So I'm going to have some extra office hours. I wanted to let you know about this. So for office hours, of course, I have them tonight after 8 o'clock. I take a dinner break at around 9, but other than that, I'll be around all evening. So feel free to come by either in person or in Zoom. Either way is good. Friday, which is tomorrow, I'm also going to be around after 8 o'clock. So you can stop by in Zoom or in person and ask me anything. And then on Saturday, which is the day that this homework is due, I'm going to be in from 4 to 6 and then also from 8 to 10. So since I don't have to teach Friday and Saturday, those office hours should be a little easier for me to handle. But anyway, my guess is you're not going to need a massive amount of help with this homework. But if you do have questions, I don't want to discourage you from asking them. You certainly should make sure that you're comfortable with this material here. Okay, so that's about all I've got for announcements. Does anybody have any questions about that? The next homework, which is number 21, that's going to be due next week on Thursday. So there won't be anything due on Tuesday. We'll wait till Thursday to get that done because it's gonna, I'm guessing I won't quite get far enough along to make that due until Thursday. So that's the next 2 assignments. And as I said, they are, I can count them all on one hand now, what we got left in these last 4 weeks. So that's not too bad. That's really not too bad. All good? Okay, super. Well, anyway, what I want to do is pick up where we had left off on Tuesday, and then we're gonna do a little group work here as well in a few minutes, but let me at least set the stage for it first, and then we'll make sure everybody's ready for the group work. We have started talking about a very, very specialized type of differential equation. So there are a lot of words at the top of the board, so many, in fact, that you might wonder, is there any differential equation out there that is all of these things? Well, it turns out that, as a matter of fact, most of the most important differential equations that you ever see in engineering are this type. They're nth order, they're linear. They might not be homogeneous, but we're going to talk about the fact that even if it's a non-homogeneous differential equation, you have to start by solving the homogeneous one first, the corresponding homogeneous one. Constant coefficients. So, right, so the nth order, that's referring to this power of d right here, the most derivatives that you see, that's the order. The linear nature of this, that's this entire operator, which the last couple classes I was calling that L. That's the derivative operator that represents the differential equation. So it's linear. Homogeneous, if anybody's wondering what that's referring to, that's the fact that we have a 0 on the right-hand side of the equation. So homogeneous just means there's a 0 here. This could be, in general, this could be f of x. And in that case, it would be non-homogeneous. So when you have a 0 on the right-hand side, it's homogeneous. And then constant coefficient, that's referring to the A0, the A1, and so on, all of those A's that are appearing in the derivative operator. So this is what section 8.2 is about. Nth order, linear, homogeneous, constant coefficient differential equations. And I think by the time we're done with today's class, you'll see that these are pretty easy to solve. This is pretty straightforward. And why is it so straightforward is because somebody way before any of us were here figured out a good so-called trial solution for this differential equation. And I put it in a box here, and you're going to want to know this. Y of x equals e to the rx. Now, what we're going to do here, guys, is guess the solution to our differential equation. By the way, I've labeled it with a star here. I'm going to keep talking about it. So e to the rx is just a guess. Somebody's going to propose that might work as a solution to our nth order linear homogeneous constant coefficient differential equation. And what we can do is we can try it where r is to be determined, and we can plug it in to our differential equation. To do that, I have to take derivatives of e to the rx. One nice thing about that is it's easy to take derivatives of e to the rx. You just pull every time you take a derivative, you're going to pull an r down in front. Just going to do that over and over and over again. So if I have to do n derivatives of e to the rx, what I'll get is r to the n times e to the rx. Right, so it's easy to take the derivatives of this trial solution. We're not guaranteed that it's going to work, but as it turns out, after you do plug that trial solution into your differential equation, and you're trying to figure out what is r, what values of r might work, it turns out that the values of r that work are exactly the solutions of this equation on the bottom of my board here. And if you notice, the way you get this equation, literally if you compare from the top to the bottom, all that has happened is the d's have been replaced with r's. It is just that simple. So you don't have to, by the way, you don't have to derive this every time. You can just take your differential equation, put it in the d notation like I have it here, and then change the d's to r's. This will be what's called the auxiliary equation, and it is an nth order polynomial, nth degree polynomial, and so it'll have n solutions. There will be n solutions for r, which is great, because the solutions for this differential equation forms an n-dimensional vector space. So I need to get n basis solutions. And I'm going to get them out of these n different values of r. It's just that easy. Let me show you on this warm-up example. just how straightforward this actually is. So in this warm-up problem, I did not present it to you in the D notation. I've gone back to sort of traditional calculus notation with the primes. But of course, I hope that everybody can, I think this was on the homework you did on Tuesday. They asked you to kind of take something in this form and write it in the operator form. The operator form is just the D notation. So the question is, can we write this in the D notation? So for the solution, the first thing I'm going to recommend that we do is we rewrite this in the D notation. So how's that going to look? You're going to put the y kind of on the right as the function that is involved in the equation. And then on the left side, you just have these various derivatives. 3 derivatives of y would be represented with d cubed, right? And then 2 derivatives of y, we have a minus sign, and then we have 2 derivatives of y, which is represented with d squared. And then I have 30 times 1 derivative of y, which would be represented with a single d, right? So guys, what I've put in blue here is exactly the same as the original differential equation. It's just being expressed in the D notation. And the reason that you want to have the D notation is so that when it's in the D notation, I can get my auxiliary equation immediately by just turning the D's into R's. Okay, so let's write it down. We can do it immediately. The auxiliary equation. By the way, how many solutions am I looking for here? Or how many solutions do I need to have? 3, right? Because this is a 3rd order differential equation, right? So I'll just point out here, n is 3. So I'm hoping I'll have 3 solutions. And let's see what happens. The auxiliary equation, I just simply turn all of the D's into R's. I don't have to change anything else other than just changing those D's to R's. And honestly, the hardest part about this topic is trying to factor your auxiliary equation. So we're going to look for the roots. The auxiliary equation should have n solutions for R. In this case, that would be 3 solutions for R. And this factors pretty nicely. I've tried to pick something that it wouldn't be too difficult. I can pull out an R. That'll leave me with R squared minus R minus 30. And then after that, I can factor the quadratic. And again, it factors pretty easily. R minus 6 times R plus 5. And it is now fully factored. And I get 3 values of R, which are 0, 6, and -5. So I'm literally just illustrating this idea that we're going to get 3 solutions for R. Now, remember that the R is coming into play right here in the trial solution. So the y of x's, the solutions that we're looking for, have this form, e to the rx. So we can now write down 3 solutions, right? So y1 of x would be e to the 0x. Of course, that's just equal to 1. We could write it as a 1 if we wanted. Excuse me. And then the second solution, y2 of x, that would be e to the 6x. And y3 of x would be e to the -5x. Okay, so there you have it. And so then these 3 functions become your basis for the general solution of the differential equation. So we can go straight to the general solution, guys. The general solution, which is what they're asking us for, the general solution would simply be y of x equals c1 times the first solution, which was 1, plus c2 times e to the 6x, plus c3 times e to the -5x. This is the so-called general solution. And you almost could have, you could have just gone straight from here to here if you wanted to. I don't recommend getting too fast and sloppy with it. But yeah, I mean, you see the 3 roots here. Then you just go write down the terms there. That's pretty easy. People following this? Does anybody have any gripes about this or anything? Did I sweep anything under the rug that I should have been more cautious about?
Tell me the difference between the homework problem and this problem. Was it the same? Because I was going to ask you about it.
The homework problem, I'm not sure which.
From last time.
Oh, the one from Tuesday?
Yeah, like the general solution.
No, there was a problem that just said write the given differential equation as an operator equation. So all that is if that would have been like doing this step. You take the original equation and write it using the D notation.
Okay.
Yeah. Maybe you can, it might be a different problem that you're asking me about. In which case, check with me a little bit later. Yeah. Anybody else have any issues here? Cause I do. I have an issue with it. I think I swept something under the rug and I'm just wondering if anybody knows what it is that I swept under the rug. It's okay, we're gonna sweep it under the rug, so it's all right, but I just wanna make sure we understand that there is a little issue here. The solutions to this differential equation form an n-dimensional vector space, a 3-dimensional vector space. So these are the 3 solutions that I have proposed, but I've just sort of swept under the rug if they're actually going to be a basis or not. What would we have to check to make sure that they actually would be a basis? Linear independence. They would need to be Li, right? I sort of didn't even mention that. I just said, all right, I'm gonna go to the right to the general solution. But I should point out that we should check that the set y1, y2, y3 is Li. So I didn't do that. I could be accused of sort of sweeping this under the rug. I really should check this. Does anybody remember the name of the test that we're going to be using in this chapter for testing for Li that I mentioned on Tuesday? I left it out of the recap. It's the W test, yeah, and W stands for Wronskian. So the Wronskian test, right? That's actually the test, and I'll just let me remind you about this test. What you do is you take the determinant of. So now how does this work? You this is already in your notes from Tuesday, but the way that it works is you lay your functions across the top row of the matrix. So I have a 1, so this is what I call W. W would be the determinant of this matrix, 1, e to the 6x and e to the negative 5x. And then I'm not sure if you remember from Tuesday, but the way that you fill out the rest of the matrix is you just go down and you take derivatives as you go. So the derivative of 1 would be 0. The derivative of e to the 6x would be 6e to the 6x. The derivative of e to the negative 5x would be negative 5 e to the negative 5x. And how long do I keep doing this? Until it becomes a square matrix. I can't take the determinant if it's not a square matrix yet. So I gotta go one more time because this is gonna be a 3 by 3. So I take another derivative. So I would have 0. The next row, we would have 36 e to the 6x. And then we would have 25 e to the negative 5x. And this is the determinant that we would have to evaluate. Okay? And any suggestions how to evaluate this Wronskian here? As I told you on Tuesday, this is a matrix of functions. So this does not have, it's not just filled with numbers. It's got functions in it, but just looking at it, what would you recommend as a good way to take that determinant? I would expand the first column. Look at the zeros that you have there. That's exactly right. So I'm going to do that. I'm going to expand column 1. And when I do that, I go down the first column, I have a 1 times the minor that's right here. And other than that, the rest of the terms of that expansion will be 0 because of those zeros. So all we're going to get is 6e to the 6x. I'm going to use the 2 by 2 determinant formula here. 6e to the 6x times 25e to the negative 5x, and then minus 36e to the 6x times negative 5e to the negative 5x. Okay, and I need to simplify that. 25 times 6 is 150. So this is 150. And if I take e to the 6x and I combine it with e to the negative 5x, I just get e to the x from that. And then I have a double negative here. And what is 36 times 5? I think it's 180. I think, yeah, 180 times, again, e to the x. And this turns into 330 times e to the x, right? Now, what was the W test? What did it say? The W test, I'm going to remind you here. The Wronskian test says, if there is a value of x, say x naught, such that W of y1, y2, and so on, of x naught is not 0. If you can plug in a number for x so that the result is not 0, then your functions are Li. That is the W test. Okay, so let me just ask you, 330 e to the x. Can I plug in a number for x that would make that not come out to 0? Anything, right? Is e to the x ever 0? No. And you're multiplying by 330, that's fine. This is never 0. Not only is there a value of x that you could use right now, actually every value of x, in this particular example at least, every value of x would have worked. You only need 1. So if you can find even one value of x, I'm calling it x naught, that makes this Wronskian non-zero, you are good to go. Okay? So that would have technically been good to show that and then come over here and say, all right, so that's a basis then, right? These 3 solutions are then the basis, and so everything is in the span of those 3 solutions. All of the solutions are made up out of the span of those 3. And that's why we can write this general solution down. So far, so good? The only way you would ever come up with values for C1, C2, and C3 here would be if I gave you a so-called initial conditions. You might remember we talked briefly about that again right at the start of the semester. If you have initial conditions provided, then you can solve for C1, C2, and C3. So just as a note, if initial conditions, what am I talking about? Initial conditions would be something like y of 0, y prime of 0, etc. I'm bringing this up because I do think on the homework there's 1 or 2 where they actually do have initial conditions for you. So y of 0, y prime of 0, etc. If those are given, then we can plug them in. We can plug them into the general solution, which is what I've got in the box here on the middle board. We could plug them into the general solution to solve for C1, C2, and whatever all the constants are. In this case, there's only 3 of them. Okay. Is everybody so far so good? Now, I'm going to give you a little bit of good news here that unless I explicitly ask you to check the LI condition here. I'm normally most of the time not gonna have you do that. This gets to be horrendously messy. Actually, the only reason we kind of lucked out here was because one of my roots was 0, which gave me a 1 for one of my solutions, and so the first column here was really nice. If 0 had not been a root, or if there had been 4 roots with a 4x4 matrix, you can see how horrendous this could get in a hurry. I will not normally be asking you to do that part, only if I specifically ask, or the question asks you to check your solutions for the linear independence. If they ask you to check it, you should, using this W test. Otherwise, we'll generally not do it. Now, just as an example of this, we're going to do some group work here. In this group work, you guys are going to show in the first problem that anytime you have solutions e to the ax, e to the bx, and e to the cx, 3 roots, a, b, and c. If you get 3 distinct roots, then the Wronskian test always works. So they will always be Li. Okay, so I'm going to let you guys try that. This is just a specific example with 0, 6, and -5. But it turns out for any A, B, and C, you'll get a non-zero Wronskian down here. So that's good, right? So we don't have to wonder about it or check it every time, because we're going to prove it right now that that works for 3 functions. Again, if there was 4 functions or 5 functions or 6 functions, your matrix would just get horrendous. And so we wouldn't imagine doing it by hand. That's my first comment. So the first problem on the group work, I'm going to have you try to do the W test for e to the ax, e to the bx, and e to the cx. The second problem on the group work is actually going to lead you through the proof of the W test. We're actually going to show that our functions are Li by running through, and that's why the group work it looks like it's a very long group work. So an entire page. It's because it leads step by step through what you need to do. I like this particular, it's a little theoretical, but I like it because it's a beautiful blending of the linear algebra, right? You see linear independence being talked about, that's linear algebra, blended in with solutions, y1, y2, y3, of a differential equation. So if ever there was a nice example of these 2 subjects kind of blending together, and being able to kind of understand that concept, it's right here, right here. So I'm going to pass this out, and I would like to give you a little bit of time with your partners around the room, anywhere you want to go, to try and work these out. And guys, there are hints in here. There are hints. You need to read them. Read these hints, okay? And I'll come around and give you guys a hand. 4, 5, 6. All right, so I'm going to erase the boards and let you guys turn yourselves loose. Grab 2 or 3 people at least, right? Everybody should have some partners. Come on down, guys. I barely recognize you. You usually have glasses.
Yeah.
Oh, okay. The glasses? Oh, I'm sorry. That's a bummer.
It was all my fault.
Oh, no. Oh, wow. Cruising along. Just go ahead and have. I mean, you can go back into either way. I recommend the arrow method. That, everyone knows the arrow. Will have either the AX, EX, and
felt.
along that arrow. You'll be able to factor it out from all six arrows. That's gonna be the trick. Right, good job so far. Right? Try the arrow method. I use the arrow method. Fix these derivatives.
All these,
Derivatives to the A axis. No minus one. You're thinking of the power ring, which is a different kind of function. Okay, sure, no worries.
Okay, so then we provide case for that.
Yeah, I mean, I don't know.
So then let's do the, so that will be a square to the a. So if
Have you done stuff on, so how are you doing?
We'll take it over.
I've just been under the weather and I was gone too long for spring break, so. Yeah. That's okay. Yeah, we'll go shoot around too.
I do have a question for you. Not pertaining to.
Okay, well, we can talk about it when we get together. That's good. Oh, wow. You guys are- Yeah, you want to multiply that out at some point. It's important. Guys, why don't you hit that with the arrow? Just use the, so 3x3. So to take that activity, we can go use the arrow method. What I want you to notice is that every one of those 6 arrows that you will do has an AX on it, and into the BX on it, and it into the CX on it. All 6 arrows, which means you'll be able eventually to pull it out. Pull it out. If you're really good, you can pull it out now. To save a little time, but if you don't feel comfortable with that, just go ahead and write out the 6 arrows, and then you'll be able to do another step. Good so far, though. How did this work out? All 6 of those have, so I yeah. Factor those out, and then see what your questions tell us. So far, so good. Come, guys, good. And all 6 of those have stuff. So I'm gonna recommend that you make those algebra steps by a factor. That'll help you to clean it up a little bit.
Cancel it.
I mean.
Just ask you a question here. Why are you doing this? There's a hint, but before we get to the hint, we do this expansion. Yeah, I want you to do the determiner so that you'll see why this has anything to do with what we're solving. So I wouldn't erase this because this is good, but somebody needs to, write out the actual Wronskian determiner.
Okay, so then,
Yeah, you
So.
So good, guys. Good work. As a C to the A, and an E to the BX, and an E to the CX.
I don't want to.
Oh, that's a data.
Nice.
Yes.
Yeah, if you pull that out now, you won't have to write it down every time. All six times. So that will make your life easier. Oh, so guys, actually, the AX, E to the BX, E to the CX, that would not be E to the ABCX cube. That would be right, E to the AX, E to the BX, E to the CX, whenever we add the exponents. This is what it actually should be.
I'm not sure about the.
No worries, it's a common problem.
Like the last two.
It is, yes. I should bring everybody in the first week, and if they can't get that one right, then I have to like do like a remedial. Thing. But yeah, it's okay, it's all good.
Yeah.
Exactly. Oh, okay, okay. You know, the first time I saw this problem, I see what is that thing in the quiz? I just. I spent an hour trying to factor, I'm like, oh, this has to like have really cool factors. I could not figure it out. It's not clear like exactly how to factor it. So I finally figured out how you're supposed to make it work. And I added that as a hit in the group work there, which is. Expand out the left side of the thing in that hit. So what you have on the board so far is good. Let's just leave it as is. And let's take the left side of that hit and just boil it out. And I know you're probably like, huh, what are you doing that for? As soon as you actually boil it out, you'll see why I'm asking. It's just pure algebra. It's just purely just the algebra. We can factor First time I ever saw this, I must have spent an hour trying to factor this. I'm trying to figure out, so we're just like, there's a piece of this, and I think that probably is going to do that. How would I, like, I used to show that this thing here is not zero. That's what you want. Oh, so it turned out that, I finally figured it out, and I added an int. Oh. And you do what like hint suggesting, you'll see how it's developed. Yeah. Let's just leave this first. I think you take it as hints. B minus A.
Yeah.
Just like same like your back. I was just like, or like, expand it. Let's see what anybody need help? Let's see what that came up with. Okay. That's the whole key. I know the exponentials are not zero. But I have to know why the part over here is not zero. Oh yeah, but you've got BC squared. So what is this? This is BC squared plus CA squared. I'm gonna write it out. plus AB squared minus A squared B minus B squared C and minus A C squared. All of that is part of this expression as well. And I will tell you, I to show that this thing is not there.
Oh.
Right, W test says, I gotta show that this W is not there. But, yeah, A with certain values of A and C. So this is not cancel out, and I was. First time I ever saw this, I was like. I spent like an hour. High school, factoring, not always speaking college math anyway. I started to fold. I finally figured out how to do it. It turned out the way you have to do it is put in the hints of this problem on the handout. So, right, if you just, let's just take a breather for what we have on the board so far. Just multiply this out. Okay?
Are you genuinely independent?
Then you're back to boil that out. And so on and so on and so on, you know what's gonna happen? And the rest of these terms are all gonna.
Yes.
So it's maybe not obvious. Maybe not obvious, but what this actually is. That's very obvious. Doing it's just out, not in care of the society. This is how it happens.
You're able to take out the C squared, or just leave it in B minus A. That would
They're distinct.
Well, then what you want to have
This is not zero. This is not zero. This is not zero. It's not zero. So this whole entire thing is not zero. That's my wrong answer.
because of the equals that.
That's it. It just spoils your fun, but that's basically, this part's just the high school outfit. So don't worry. All right, fantastic. Anybody need help? Did you guys multiply that whole thing out? Okay. So here, okay. So you got A squared B, right?
I don't think.
Wait a
I don't think I squared.
Did you multiply this? I have a minus A and a minus A, shouldn't this be plus A?
Oh, everything is,
Everything, no, it's just, I'm just gonna mess these two. So A, so this should. Negative minus, this should have positive. I think that's the only thing. Well, there's negative A squared. There's negative A squared. There's positive, right? A squared C, there's positive A squared C. AB squared, JB squared. Minus CB squared, minus CB squared. C squared B is that, minus AC squared is that.
yeah.
So this thing that you were trying for 10 minutes to factor is actually C minus, B minus A times C minus A times C minus B. That's how you factor it.
Right. Which doesn't.
It doesn't equal zero because they told us that all of the roots are distinct. They're distinct. So A does not equal B, A does not equal C, and B does not equal C. So that's not zero, not zero, not zero, and neither is this.
Right.
Nothing is zero, and so your W is not zero. That's the wrong scale test.
Oh.
And you're done. You're done. That's the whole ball of wax. Did you hear what I just said? Does it make sense? Okay, we go on to number 2 then.
Extend it over. We don't know that. I can do it, and then.
This thing factored as a little bit. That's why I was showing those guys over there. It turns out, I'm gonna spare you the details because I want you to move on to the next problem. But this is actually B minus A times C minus A times C minus B.
Okay.
Okay. So that's how it factors. And the thing is, they told us in this problem that the roots are distinct. A, B, and C are distinct, which means this is not zero. This is not zero. This is not zero. And neither is this. So these thing all the way across. As long as the W is not zero, the function for L high. That's it. I tried to do this. I also tried this problem. Before I saw how to do it, I was fumbling around with this forever. I could not. I felt silly. Like, this is like high school. The factory, I can't even do it. I was like, oh, this is not really the right way to get this back. This is actually.
How did you know?
Many years ago, I found a piece of this. And I just experimented with this. If you know this is the right thing, you can boil this out and recover what you have here, and then you can confirm that you can. Yeah, that's it. Okay, you guys ready to go on to number 2? It looks kind of long, but each little part.
Yeah.
Just hang it there. Each part is very short.
Are you doing
We need to branch to the equation. What equations we get? Should we write it?
Yeah, so it's no, no, it's not very example. One of them.
Yeah, so should we?
Yeah.
Oh, yeah.
Yeah, because it says, yeah, because it like, what do you do? Once, twice, and then three times.
Focus like this one.
Yeah.
I don't mind
So that, so should.
When we're talking about
My dad.
I think that it's actually. If you write it, there's.
Yeah, so write it, instead of y, write it like.
How about linear combination? Equal to 0. You wrote that.
Differentiate y.
Anyways.
What is linear independence was the only way to cancel out what that problem of linear combination. That all of that nonsense are.
Maybe like.
So the thing is to show what's proof is that all responses, C1, C2, C3.
Will you just factor out the C?
And then we would take first.
That's what I was before on part A.
C's a constant. So if you go C.
To show all of the constants are 0.
Yeah.
Okay, you can't factor that, Aaron. There's the constants are all different. It's not the same C everywhere. Nice, looks good. You guys can erase and try number 2. Do you guys
Oh, like,
linear independence?
Okay.
I see everything's, that's like many moons ago. Just the vector space chapter. If a set of vectors is Li, what it means is the only way you can cancel them out in a linear combination, which is what you're saying, right? The only way that that can happen is if something about the constants. The constants must be
Equal to each other.
start.
Zero, yeah.
There you go. Yeah, sorry, it must be. Must be. So in other words, the only way to cancel the vectors out is by sort of cheating and putting zeros in front of all of those.
Yeah, so.
The only way, what Li means that you cannot find any interesting linear dependency. The only way that these vectors can cancel out. Oh.
Yeah, so C1.
That's what that is. All of the constants are.
Yeah, exactly. Yeah, that's it. Yes.
You guys comfortable with all this?
No.
The whole definition of linear independence takes us back like a month and a half or more. But what it was that a set of vectors is Li means if they cancel out in a linear combination, which is what you wrote on the first line. I said if they cancel in a linear combination. The only way that should happen is by sort of cheating and putting zeros in front of all of the vectors. So that would mean C1 is 0, C2 is 0, C3 is 0. In other words, there's no interesting linear dependency. You can't like create some interesting combination of Y1 and Y2 to get them to cancel out. The only way they can cancel out is with all of them on 0. So that's what you're showing in this 6-part derivation. And by the time you get to part, or 5-part derivation, by the time you get to part, how can you now conclude that C1 equals because that is what you want to show. That is what I mean. Feel a little better about it? Like, it is a few weeks old. We got a question here.
Because.
What would be the?
We'll start by.
Take a derivative of, if you don't, so you just do a bunch of equations. So you, right, that looks awesome. Good job. So far, so good. I like it. I like it. Okay, yeah, that's it. That's it. You got it. You got it. Yep, all the constants need to be 0. And if you look by the time you get to part E, at the very, 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 very bottom of the handout, the last thing is gonna say, how can we conclude that C1 equals C2 is not equal to, that's where you're going. That is where you're going. Oh, you should be taking derivatives there.
Oh, okay.
You should be taking derivatives. So C1 Y1 plus C Y2 plus plus C and YN equals 0. You need to take, just literally take a derivative.
Oh.
Right? And then do it again.
Okay.
Now you got the second derivative here.
Oh.
Yeah, and how many did I say? N minus, so this is dot, 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 right? Eventually you'll get N minus 1 derivative. Yeah, look at that, so fast.
Yeah.
So there's your system of equations. And I think from here, the next question is gonna be asking. Okay, great. Anybody need help?
So this.
I was thinking something.
Right, so what happens if you take the derivative? I'll do the right hand side. Derivative of 0 is just 0, right? What about on the left side? Well, it's just the prime column. You just end up with derivatives.
Oh, yeah.
And then it asks you, what happens if you take derivative twice, right? Well, that's just another, yeah, it's a double derivative, right? And I think it says to do it n minus one time. Just keep going like that.
What is this? Yeah,
And if you take all of these together, then I think you'll be ready for part C, which says to figure out how to re-express this as a matrix. If you can re-express it as a matrix.
Yeah.
Oh, dude. What is A and what is, make a matrix here?
Oh,
So,
It's the
that last line here, guys, that and white. Yeah, that's actually, you know, it actually doesn't. So what you have to say about this guy, so everything above me. The animals. That's perfect. You're doing it exactly right. That's exactly it. Nice, nice, nice. Did you guys get it? So when I see it written like this, that looks like a line one, is an entire column. But line one is just a scalar function, like just EDM. So it doesn't really fill the entire column. What I would say is, I like that you've done this part correctly, C1, C2, up to C now. And you've got all these zeros here. Right? But let's just go back to the first equation. How could I, do I have to do matrix multiplication? So go across the rows here and down the column. So what do you think this first row is? Y1 times C1 and then Y2 times C2 and so on, right?
The determinant, I think.
So what about this thing? Same thing, but with the derivatives, right? Are you starting to see the Wronskian show up? Okay, maybe just keep going like that.
Oh, because we're the next.
And so I think part C, this is the capital A, this is the C vector, and that's how you set it up. But this capital A isn't just in your unit major. This is our friend that we just learned about, which is the Wronskian. You have to think that. Good job, good job.
Yes. How is the matrix equation?
That is exactly it. The matrix A is the vector with the drawn in the column on the right side of that. If you're doing dot product, right? And that's all equal to the derivative. So are you seeing the Wronskians starting to show up now? It's just that matrix on the left. Oh, yeah, that's right. Yeah, no, what you have up there is also correct. But here what we're doing is we're re-expressing these equations as a matrix multiplication. Right? This is a matrix multiplication. So now, if the Wronskians determined that that's all right, it's not zero. Right, this means that this matrix is invertible.
Oh, wait, no. So. I think.
I have an equation where my matrix is invertible.
Because of the
Then you can use an inverse. Cancel it. Now, only with C on the left and on the right, you have a inverse. So you have a zero. The inverse times zero. That's all zero. This vector is just zero, that means all of these zero. Just stole all your photos. I get excited. Yeah, does that make sense? It's a nice chance to review some of the linear algebra. And then X, you're welcome.
We can say for D, we can say.
Out there on the left. Ross is.
That's the. Yeah.
That's one way of saying that A is invertible matrix. If it's invertible,
No, actually, using that option, now they put the bottom. No, actually, that makes.
Right.
Yeah.
Because this A is invertible. It's not A inverse. Both sides of these. So look at your left here. All of those values are zero. There's not. We were trying to prove all of the constants are zero. That's what this. Hey guys, I'd like to go ahead and give you like a 10-minute break. So if you want to step outside, grab some fresh air, anything like that, this would be a great time to do that. In about 10 minutes, we're gonna pick back up again and do some new material. So. It's good. You guys basically get it? Okay, great. Great.
Yeah.
Yeah, there's no big deal. Yeah, like 451. 451. So you can take that. Yeah. Those are the only way you can get. Yeah, you're using. So do you take these? Are you? Oh, holy, what did you send me? It's engineering statistics. Oh, I already took it. I already took it as soon as that. Oh, fuck, no, okay. The one that you're talking about, I already. 3, 4, 3. We're taking one of them. Yeah. This one. Probably, I think so. Oh, yes. I think so. I just talked to him today, so my registration was tomorrow, so. I think it's looking like. All that shit. I know, it's like it though. Yeah, I should have been taking this kind of second. So we're in there for 371. It says Spring only, fall. No, no, you wrote it. Like that's on it.
Are you feeling? Real.
You know, I'm so stressed about now. Cause I'm already struggling in 2 or 3 some like days.
And it was still there, it's still that is still on.
Wait, really?
He worked right here. Real is only a block.
No, that's what I'm saying.
Oh, okay.
Yeah, bro, you see me, bro. I was like, dude, if I fail it.
Oh, okay, never mind. Never mind.
Yeah, it's the red and red. Yeah, you can do it. For sure, bro. That shit's sick. It's
It's a meeting thing, that's my main thing.
Yeah, you're taking grades and grades. Something else.
Yeah.
I swear there was a difference here. Like, they were being taught.
in the semester added to ND. No, I added it to my part. My scheduling was good.
I don't know. It only shows you. It only shows you. I'm just thinking, if it's in your part, it doesn't matter. There's something else.
I think it would make probably another.
Oh, I'm gonna take two. Yeah, bro. That's what I get. Market. You're cool. I was like, so that's the thing.
Now we take out it's also my house for 2 days out.
There's only 4 classes.
No, I know.
Just make like 1 or 2 weeks in the end of the 5. 1, 2.
No, we found so.
Bro, you're tripping me out, bro.
So for the next semester, I'm going for like 6 or 7 I'll drop it, I'll drop like one of them like later on, but I wanna take it and like, you know. I don't have an option.
Only use anything.
It's here, right?
18 or 20.
The fact that really only has 1 section, okay, it's scary. I know. It's a show how many people.
What's the worst thing you have?
So they have EPN 4.5, which is like it's the intern. So you know, but then you have to sign up for it. And you don't even need to make it. They'll give you like some information, but I have to sign up for this time. But then I have like $1,000 for that.
So you gotta pay them for the intern.
Yeah, exactly. Why? I ain't gonna do that.
You don't get paid for nothing.
Yeah, exactly.
So you pay to register.
Exactly. And then I think they put camera on talking out with the apps, like the actual second.
Once I go into next semester.
I'll take work.
I'm sorry to hear that.
Oh, thank you.
Like what?
Did you have a big family gathering or?
Yeah, it was on my dad's side and I had 6 kids, so I have, yeah, it was a big family.
So you know a lot of people from that group.
Yeah, it was actually really nice that,
Consent.
her funeral has like 400 people there.
Oh my gosh.
Yeah, it was,
She must have been really well known.
yeah, she was actually, in East LA, she was a, seamstress. So a lot of people who she did like, wedding dresses or
Okay.
fixing hairs and stuff like that, they went.
They knew her.
Yeah, yeah.
That's really something.
Yeah.
Also, my mom says to me, I'm trying, you must graduate now, with 4 years in the kids classes.
I don't do any type of, I'll still be like, I need 1 more so that I can.
I think one person can do the classes, so.
One person hard, but I mean, just administration. Those guys are so chill.
Depends on one class of level for, okay, I'll be.
But then I'm like, bro, you might get paid better than them.
Look at figures. I was gonna say. What? So it's taking 5 years already.
Yeah, 18 minutes.
So I'm just gonna burn myself out.
I would have taken both. But this is an offer and. I don't know, I'm sure that. We should do number 18. It's full.
Like, just get black.
No, no, is that something that you know, that like, it's just, you can take any like after 12, just take like, you know, whatever you go and like, yeah.
That's the same idea. It's well, you just see the difference between your goals and projects.
Yeah.
You watched the Masters golf tournament
Did
you?
Uh-huh.
for 4 days?
Yes.
Oh, wow. You're dedicated.
Ouch.
Did you fall asleep? No?
No.
If I did that, I would fall asleep. I
I
did not actually watch the whole thing.
Because I had 150 bucks on the limit.
Oh, that explains. it. Okay, I thought you were trying to like pick up some tips.
Well, I do for that, I'm also gonna have 150 bucks on the limit.
I see, I see. You were,
Payout's pretty big, so I'm not complaining.
no, for sure. That's like the biggest golf tournament for the year, I think, pretty much, yeah.
Yeah, I haven't probably done the golf once.
All right, guys, I think I'm gonna go ahead and pick things back up again if I could. Thank you for your diligence and hard work on the group work. Just a quick reminder, the solutions to these group works are in Canvas, and we did group work 11 on Tuesday. Today's group work 12. These are worth reviewing, right? Even if you feel like you really understood everything right now, a few weeks from now, maybe a refresher would not be the worst thing. So I just want to remind you that those solutions are up there, and you can and should review them as much as you need. Now, I don't know if anybody's thought about this yet, but here's the deal, guys. We have an nth order differential equation, and I need n basis solutions. Right? E to the ax, e to the bx, e to the cx, whatever they are, I need n of those. But the problem is, what if I just get the same root? I'm gonna get n roots, but that includes repeats and complex numbers. And the question is, what am I gonna do if I do get repeats and or complex numbers when I factor this auxiliary equation? And so both of these are issues that do come up. And so I need to address them both. Okay, does that make sense? Like on the group work, it was assuming that all the roots were distinct. Okay, and on that warm-up example, the roots were all distinct. But it's possible, it is very possible that you could have repeated roots and or complex roots. And the question is, how do you deal with those kind of outcomes? So let's take them one at a time. I'm going to start with number 1 here. Repeated roots to the auxiliary equation. Okay, so let's get into it here. Let's come back and talk about number 1 right here. Turns out that, again, somebody way before any of us and way smarter than me figured out how to address repeated roots, because we do need n different linearly independent solutions. So how are we going to get those? Well, here's the answer. If a root R is repeated k times, so it's like it has a multiplicity or a weight of k, then we can get k linearly independent solutions to the differential equation. I'm just going to put a colon here and I'm going to write them out for you. Okay, so y1 of x would just be, e to the rx. But see, guys, I can't just write down e to the rx again and again and again. That would just be the same vector over and over and over again. That's not going to be li. So we have to figure out a little trick to how to get additional solutions here. And the trick is to start stacking x's in front of this expression. So I'm going to do x e to the rx for the second solution. For the third solution, I'm going to go all the way up and stack x squared in front times e to the rx and dot, dot, dot. The kth solution, I'll call this y sub k of x. This is going to need to be x to the k minus 1 times e to the rx. Now, you can imagine that trying to do a Wronskian on stuff like this is not going to be fun. Because you actually, to take even one derivative of any of these individual functions requires the product rule. And so product rules upon product rules upon product rules, by the time you get down to the kth row of this matrix, you're gonna be ready to like go jump off a bridge or something. It's gonna take like all night. It's not going to be fun. So we're not going to do that. We're just gonna take it on faith that if we did the Wronskian test, that we would get these linearly independent solutions. So this is what I like to refer to this as the X stacking method. Very simple. You just need to learn it and know it. And when repeated roots come up, and they will, that's how you handle them. Okay, so if we get repeated roots, and we will look at an example, but I'm going to wait to do an example until after I've talked about the second issue. So we're going to move on right away into the second issue unless there's a question so far here. Everybody okay so far? So we're stacking x's in front of the e to the rx. So by the way, sometimes I'll have students say, aren't these scalar multiples of each other? Right? They're supposed to be Li, they should not be scalar multiples of each other. Well, x is not a scalar. A scalar would be like a specific number, like 3 or 7 or something like that. This x is not a scalar creating scalar multiples here. So these are actually going to be Li, and that is the way of creating linearly independent solutions in that case. Okay, so let's go on to the second issue. The second issue is a little more complicated. What about complex roots to our auxiliary equation? So if R is of the form A plus or minus BI, where B is not 0. So I'm going to imagine that we actually have a legitimate imaginary number here. These roots, by the way, they always have to come in pairs. You cannot have A plus BI as a root without also having A minus BI as a root. That's going to be for sure. So I can kind of think of this as two roots. And what we're actually going to do, guys, is we're going to make two solutions that go with those two roots. So instead of sort of 1 for 1, where we have one root and we make one exponential solution, then we have another root and we make another one. Here, instead of 1 for 1, we're going to come up with two solutions for these two roots. So it's a 2 for 2 sort of correspondence, if I could call it that, right? So this is the idea. So we generate two solutions. And I'll put another colon and talk about how to get them. Now, you might think that I would call the two solutions y1 and y2. I'm not going to do that because ultimately what the first thing I'm going to write down is not going to turn out to work. So this, as I said, this is a little tricky. So I'm going to call this Z1 and Z1 of X, sorry, and Z2 of X. Okay. Now, how would we normally make the solution? Well, the first solution would be e to the a plus bi times x, and the second solution would be e to the a minus bi times x. That's just in keeping. That's just in keeping with the general trial solution that we started off this section talking about. Okay, so this is what we would have. Now, the only problem with this, so you might think, well, what's wrong with that? There's your two solutions that go with these two roots. Isn't that good? Isn't that good enough? Well, guys, many of you are engineers. You're solving real world problems. You are not solving problems that have imaginary numbers in them. If you go hand this to your boss might not like it too much. For one thing, I don't even know how to plug in. You plug in a number for X here or something? I wouldn't even know how to use my calculator to calculate e to the 5 plus 7i. I don't even know what that would be. How would it be presented? I also wouldn't have any idea how to graph this thing, right? Because your input is, your x here is going to get multiplied by a plus bi. Your output is some weirdo thing. I don't even know what that would look like. I wouldn't have normally what your boss is going to want is something like this. C1 of x is this picture. That is not what that's going to give you. You won't even be able to use a calculator to get values. You won't be able to draw a graph of it. So this is unacceptable in the current form, right? It's unacceptable in the current form. We've already seen an example of this. Do you remember the one that we did on Tuesday? You don't need to write this down. It's already in your notes. This one here was the one that turns into d squared plus 1. The auxiliary equation becomes r squared plus 1. You just turn the d's into r's. And the roots of this are plus and minus I. So we have imaginary roots to this problem that we did actually on Tuesday. Of course, on Tuesday, we didn't talk about imaginary roots. I just asked you, does anybody know of a function where two derivatives of it cancels it out? And does anybody remember what the solutions were? Sine of x and cosine of x, right? Oh, so somehow maybe we should be expecting to have sines and cosines coming out of these two expressions here. Let's see if we can work on them a little more and see if that might happen. So let's just go a little further. Now we can come back to the notes and let's see if we can get this cleaned up a little bit. This first one, I'm going to write it as e to the ax times e to the I bx. And then on the second one, I have e to the ax times e to the I times negative bx. So carefully using my laws of exponents, that's what I would need to have. Okay. Now, I'm going to put a little asterisk here. I would come over here for a minute. Does anybody think they might know how we can evaluate e to the I theta? Because I see the e to the b I times bx here. So this is a formula that you might have seen before, and this is where the sines and cosines show up. So this is a famous result called Euler's formula. And have you seen it before? Omar, what is it? Do you remember?
Going to be a cosine theta plus I theta.
That's it. Yeah, cosine of theta plus I times sine of theta. That is Euler's formula. Probably the best way I know how to prove that formula is to use the power series. Oh gosh, dare I say that in this class? The power series representations of exponential function, cosine of x and sine of x, and you can just calculate the power series of all three of those and match up the left side with the right side. We're not going to do that here. That's not really the focus of this, but if anybody's interested in it, I've got plenty of time in my office hours. We can hash it out. But that's the Euler's formula. Maybe some of you have seen the famous T-shirt. We had a math club T-shirt one time that had this equation on it. If you plug in theta as pi, then cosine of pi is -1. This is like a famous equation that involves e, I, and pi all in the same equation. And so it's kind of a famous one that maybe you see a bumper sticker with this on it or a T-shirt or something like that. In my dream world, that's what it would be. But probably it's not that famous, but I like it. But I'm going to use it right now, guys, to simplify what's going on the lines that we have here. So can I erase the Euler formula? Actually, I'm going to erase it because I'm going to recopy it right here. So let's come back. I'm going to keep going. with both of these lines. So this is e to the ax, and then the next part is cosine of bx plus I times the sine of bx. All right, and then the next one is e to the ax times the cosine of negative bx plus I times the sine of negative bx. I just fill that in. Notice that I'm still not satisfied with what I have because there is still an I in that expression, right? I still see an I right here and here. Let's go one more step. I'm just going to expand it out. This is really e to the ax cosine of bx plus I times e to the ax sine of bx. Okay? So I just distributed the e to the ax there. On the second line, I want to do the same thing, but can somebody remind me, cosine of negative theta and sine of negative theta, does anybody have this trig in their mind? If you think about the cosine function, it is an even function, meaning that if you plug in the negative of theta, it's the same as just plugging in theta itself. Whereas the sine function is an odd function, so if you want to pull the minus sign out of the sine, you have to do a sign change. So I'm going to do that here on the second line. This is going to be e to the ax cosine of bx. But now I am pulling out the minus from the sine, and when I do that, it switches the sign on the outside. It becomes minus I times e to the ax sine of bx. With me? So with these two roots, guys, we can make these two solutions. Neither of which is acceptable yet, right? Both of them still have an I in them. Is there a way to make an acceptable solution, though, out of those two unacceptable ones? An acceptable solution would be one that does not have I in it. And right now they both do. Could I do something with these two solutions that would make the I go away? Yes. Can we add them? Oh, right on cue. Guys, remember closure under addition, right? Solutions this is the kernel of L. It's a subspace, right? The solutions form a subspace. So if you've got two solutions and you add them together, you have to get another solution. If I add these together right now, what will happen is the imaginary part will cancel. You just literally vertically add these and you'll get two copies of e to the ax cosine of bx. So what we're going to do is exactly that suggestion, which is we are going to form the solution. Now I'm going to call it y1 of x. And the way we're going to do this is we're going to take z1 of x plus z2 of x. And just because I don't want that factor of 2 to kind of get in my way, I'm going to use the scalar multiplication that's available to me as well. A 1/2 scalar is perfectly fine. And by the time I've divided through by 2, guys, I will have e to the ax cosine of bx. There it is. There it is. Right? So that's one solution that your boss will accept, right? That is a function that I can graph. It does not have imaginary values. And because of closure under addition and scalar multiplication, it has to be a solution just as much as the original Z1 and Z2 are, right? Now, that's one solution. I also need to form another one. Wondering if anybody knows how I'm going to get my second solution. Instead of adding the two things I see right here, can I do something else? I think I heard it. What was that, Antonio? Subtract. I could subtract them. Now, if I subtract them, this part will cancel. When I subtract them, I'll get this one minus a negative. I'll get 2i times e to the ax sine of bx. But I can use the scalar. Now, we've never done scalar multiplication with a complex number before, but there's no reason why we can't. And that is exactly what we're going to do. We subtract those two functions, and this time we're going to divide by 2i, and we get e to the ax sine of bx. So my friends, I have just derived for you how we get two real solutions out of a pair of complex roots. So like on this example here, when r was equal to plus or minus I, I'm going to do more examples in a second, but just since it's already on the board. If I look at plus or minus I, that would have an a value of 0 and a b value of 1, right, for this pair of roots. And so what would be the solutions? If a is 0 and b is 1 in those two boxes, what do I have? Cosine of x and sine of x, which is what we said on Tuesday when we did this example kind of grassroots approach, right? So absolutely right. We can just derive our solutions using this. Okay, anybody got any questions on that? All right, so the last time I taught this class on the third exam, I think I did a 14th order differential equation. So I think I'm going to try a 14th order example with you right now. You ready for this? We've done a few first order, second order, third order, right? Let's go big. Go big or go home, right? That's what they say. Ready for this? Here's the example. Oh my goodness. Find the general solution to, so let me give you this differential equation. D squared minus 6d plus 13 quantity cubed times d squared times d plus 5 cubed times d squared plus 4 of y equals 0. By the way, in the homework, they won't be nearly this big. But actually, it's not that hard. I keep talking about this section like it's, all you got to do is change the d's to r's. Okay, so I've already kind of factored it for you. That's what, if I if this had been multiplied out on the left side, then I would say, yeah, that's a really hard problem because I don't know how to factor it. But this one is mostly factored. This one is mostly factored. Our auxiliary equation, let's write it down. Our auxiliary equation. Can somebody remind me again, how do I get the auxiliary equation out of this? You change all the d's to r's, exactly. So my auxiliary equation will be r squared minus 6r plus 13 quantity cubed times r squared times r plus 5 cubed times r squared plus 4. We set that equal to 0. Whoops, this should have been a times right here. Oh no, this is only a 13th order differential equation. We can fix that. The d squared, let's jack it up here to the third power. Let's change the power of d to be third power. I promised you a 14th order differential equation today. Go home and tell your friends, Dr. Annan is teaching us how to solve 14th order differential equations in his class. Okay, so now we have to get the roots. This first one is a quadratic, so I can use the quadratic formula to sort of solve for the r for this. So that's going to be what? 6 plus or minus the square root of 36 minus 52 all over 2. And so let me just start with that. 6 over 2 is 3, and we have plus or minus. This is the square root of negative 16, which would be 4i. but that gets divided by 2, so it's 3 plus or minus 2i. Now, guys, remember I talked about this before, when we were doing the eigenvalue chapter. If there are repeats, you need to write down those repeats as many times as they repeat. So 3 plus or minus 2i, see, it's cubed here. It's cubed. So this 3 plus or minus 2i has to be written down 3 times. Those complex conjugate pairs have to be written down 3 times. Now, what other roots do I have? I have r cubed, that would be 3 zeros. And then I have r plus 5 cubed, that would be 3 factors of -5. And then r squared plus 4. You could use the quadratic formula if you needed to, but you probably know that the square root of -4 is 2i, plus or minus, right? Plus or minus. So now we have to count how many roots do we have, just to be sure we got it right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 14 roots. It is a 14th order differential equation. Okay, perfect. So now, you know what we're gonna do now? We are gonna go straight to the final answer. This is how this section goes. You find all the roots and then you just write the answer. Okay, so I'm gonna do the first one, and then 13 of you are gonna do the rest of them. I'm gonna start picking on people. So we'll see how it goes. Ready for the general solution? So let me do the first one. Y of x equals, so the first term would be C1 times, and I'm just gonna go in order. So I'll start with the first one, the 3 plus or minus 2i. All right, well, I know how to handle the complex numbers right here. So the first one is gonna be e to the 3x cosine of 2x. Give yourself a lot of room to write this down, by the way. There's going to be 14 terms in your answer. Okay. Does anybody want to volunteer to tell me what the next term of the solution would be? Go ahead, Andy.
The same, but just -2x. Like C2 E3x cosine. Oh, sine, sorry.
It's right here. Yes, sine of 2x. You got it. You got it. Sine of 2x. Perfect. Okay, sweet. That's the next term. Okay, only 12 more to go. Now for the next term, so I've already handled that complex pair. Let's go to the next one. Now the next one is the same complex roots. In other words, it's repeated. So what did we learn about repeating roots? This is this thing about stacking x's, right? So with that in mind, does anybody want to take a gamble on the next term? Go ahead, Alex.
C3 x x cosine 2x.
Nice. C3x e to the 3x cosine of 2x. I've stacked an x because it's a repeated root. Okay. Anybody want to try the next term? C4x e to the what? 3x sine of 2x. I like it. Okay, so that handles that pair. Now we go to the next root is the same one again. 3 plus or minus 2i again. Do I have a volunteer for the 5th term?
C5,
Go ahead.
C5 x squared e to the 3x cosine.
Nice. Exactly. Now we have an x squared there. Through stacking again, another power of x. Okay, volunteer for the next term? Somebody I haven't heard from yet? Go ahead, Tiffany?
C6 x 2
C6 x squared times what?
3x
E to the 3x
2x.
sine of 2x. Okay, super. I like it. So that takes care of those roots. let's keep going. Now, the next root is just a 0. So now we're kind of on a new root that we haven't seen so far. So this next term is gonna look quite different. Does anybody have an idea what the next term is going to be? Remember, it's really e to the rx. So if r is 0, then that's just 1, right? And of course, we have to have a constant. Every single term has a constant in front of it. Let me call it C7. It's just C7 times 1. Exactly. Okay, so that's 0. Anybody want to try the next root? Or the next term, I should say. C8 x. We're stacking an x because the 0 is repeated. And that's it. Okay. What's the next term? C9x squared. Sweet. Looks good so far. And now we come to the next root, which is -5. Somebody want to try that one for me? Stefan, do you think you know?
C10 e to the -5x.
Nice. C10 e to the -5x. That sounds good. James, do you want to help me with the next term? If you don't, you don't have to, but.
C11
Uh-huh.
E. Stack of X,
Got a stack of x.
Yep.
And then
-5.
-5x. Beautiful. Yep. C11x e to the -5x. That looks good. Who else haven't I heard from yet? Omar, have I heard from you? I don't think so. You want to tell me the next term?
So it would be C12
Okay.
and it would be x to the second
X squared.
and e to the -5.
-5x. That's it. Sounds good. And we have almost gotten to the end. That takes care of the 3 repeats of -5. And the last pair of roots I have over here, guys, is plus and minus 2i. Does somebody want to try me out on the next term? Plus and minus 2i. So there's no real part. That just means that a is 0 in my imaginary number notation.
C13 cosine.
C13, I don't know who's talking to me here. C13 cosine of 2x. Exactly, guys, it's e to the 0 times cosine of 2x. Because this is just 2 plus and minus 2i. Okay, and then the last term is going to be what? C14 times sine of 2x. Guys, the cosines and sines always have to go together. Do you realize that it takes more time and space to write down the answer than it does to solve the problem? Yeah, that's it. That's how it works. Now, if I really didn't like you very much, I'd make this into an initial value problem and let you solve for the 14 constants that are here. But that would really be ugly. Or if I really didn't like you, I could say, check that those are Li. Let's make sure they're linearly independent. And you could do a 14 by 14 Wronskian. Oh, how much fun would that be? Right, so that would be nuts. But you see, guys, the process, pretty easy. So the ones on the homework are much lower order, much easier to do. This is it. This is really what the homework for Saturday is about. But they are much easier. They're like 3rd order, 4th order. The hardest part sometimes is just factoring the equation. Now here it was given to you already sort of factored, right? So that makes it easy. In other problems, it might not be presented as a factored equation and you're just going to have to deal with it. So far, so good? We are going to get more practice on this because in the next section, which I'm going to start right now, I only have about 10 minutes, but I'm going to start the next section. We have to keep doing this same thing again, a little bit more. So are there any questions before I go on? So just remember, with repeated roots, we do this x stacking business. And with imaginary roots, we form e to the ax cosine of bx and e to the ax sine of bx. You just have to kind of learn that kind of as a reflex, after you've done a few of these problems, that probably will just come to you naturally. Okay. Well, we've addressed those two issues, and that's about the whole story on nth order, linear, homogeneous, constant coefficient differential equations. But the fact of the matter is that in real life, and I think next week I'll actually show you some engineering examples. I'll bring them, I may not focus on it, but I'll at least show you where it comes up. But in real life, very often the differential equation is not actually homogeneous. There's some kind of forcing term. There's something sort of external to the system that drives the system. And you have to account for that. And so we have to go back to study non-homogeneous differential equations, and by which I mean L of y equals F. We have to bring this capital F back in. As I said, I sometimes think of it as what's called a forcing term. In physics or engineering, you might refer to it in those terms as well. And so the goal here is still the same. The goal here is still to solve for y. And there is what I like to refer to as a 3-step process for doing that. So I'd like to give this to you. We are not going to have enough time to really do one of these today, but that's okay. It'll get you motivated to come back next week. But I at least want to get the outline of the process. There is a 3-step process for achieving this goal. The first step of this 3-step process is to simply change this F to a 0 and go back and do the homogeneous differential equation, which is what we've already been talking about all day today. Right? So step 1 is solve the corresponding homogeneous differential equation, which would be L of y equals 0. So just forget about the capital F momentarily. And when you do this solution, it has a name. It's called the complementary function. So the solution here is the so-called complementary function. You'll hear me use that name quite often, so I just want to get it up here for you now. And I'll be denoting that as y sub c of x. So the complementary function, just a little box here, is just going to be denoted as y sub c of x. So in this problem that we just did, this 14th order differential equation, this would be the y sub c of x because it's the homogeneous differential equation that we just solved. Okay, so that's step 1. We already know how to do step 1. Well, I should qualify that. We've only practiced it once, but by the end of this next homework, you will know how to do step 1 really easily. So step 2 is the new part, which is that we have to find what's called particular solution. And this is denoted y sub p of x to L of y equals F. And I'm just going to, over here again, put a little side comment. I'm just going to asterisk that and say see below. I'm going to explain below how we actually come up with one particular solution. You only need one. You don't have to find a whole big family of solutions like we did there. I just need to find one particular solution. So I have to explain how we can do that. And then finally, the third step, as I said, it's a 3-step process, is that we can go to the final answer immediately once I've done those 2 steps. Namely, the final solution is just y of x equals y sub c of x plus y sub p of x. You literally just have to add them together. You just have to add the two things together, and that gives you the final solution. Okay, perfect. So step 3 is a no-brainer. You're just taking what you did in the first 2 steps and putting a plus sign between them. Step 1 is kind of old news, so we already have learned how to do. It's really just step 2 that we have to talk about. Everybody with me here? Am I hopefully not making anybody too dizzy with where we're at? The idea is that most differential equations have some kind of a forcing term. And so what we have to do is first solve the associated homogeneous differential equation, and then we got to deal with the forcing term, and that's what step 2 is about. Okay. So we kind of go back to my asterisk here. For step 2, there are 2 different methods that we are going to learn. Excuse me, we have 2 methods. The first one is called annihilators. And this is covered in the next section, 8.3, which is what next Thursday's homework will be about. So annihilators. And then the second method, we need 2 methods because neither method is always going to work. So we'll discuss that issue a little bit. The second method is something called variation of parameters. And that is covered in the book in section 8.7. The intervening sections, 8.4, 8.5, and 8.6, we will be skipping because they are basically going to be the stuff you'll see in your engineering classes. So in your engineering classes, you'll see in the intervening sections, they'll talk about electrical circuits. They'll talk about mechanical systems, spring mass systems, and all this kind of stuff. So I don't feel, I'm basically charged with teaching you guys the math behind it. And then in your engineering classes, you should see the applications in more depth. So my main goal for next week especially is going to be to try to make sure everybody understands these 2 methods. How much time do I have left? I'm over. What? Well, then I guess we're done. We'll come back and talk about this next week. Don't forget, I have office hours the next 3 nights. If you're working on the homework and you get stuck on anything, I'll be glad to help you out. Have a great rest of your Thursday, everybody, and enjoy your weekend.
Thanks.
All right.
Are you gonna do that?
See you.